Chapter 13, a short little introduction to gravitation. Up until this point, I've said that the Earth is going to exert a force on you, and that force is going to be your mass times gravity. It turns out that that is only true near the surface of the Earth, which has been the cases that we've been looking at up until this point. But it turns out if you get further and further away from the center of the Earth, the force of gravity will get smaller and smaller. So it turns out that every particle of matter is going to attract every other particle of matter simply because they have some mass to them. The force that a particle is going to feel is going to depend on its mass as well as the mass of the other particle that is attracting it and exerting a force on it, and it's also going to depend on inversely on the square of the distance between them. Kind of a mouthful. We can express this mathematically by saying that the force of attraction between objects is going to be this gravitational constant g, which is simply a constant of proportionality, which is going to be 6.67 times 10 to the negative 11th newtons meter squared per kilogram. The force is also going to depend on the mass of the first object, and it's going to depend on the mass of the second object, as well as the square of the distance between them. That little r is not going to be the radius of either objects, the Earth, or anything like that. It's going to be the distance between two masses that are attracting each other. You can kind of see, because this value of g is very, very small, that you're really not going to feel the force of the computer screen in front of you, simply because you don't have a lot of mass and your computer screen doesn't have a lot of mass. If we start talking about things like the Earth, which has a mass that's 5.98 times 10 to the 24th kilograms, then we can start saying, okay, we're going to really be able to feel these types of forces. But even though you may not feel the force of attraction between you and the computer screen, it still does exist. Something else to kind of consider is this mass is going to be exerting a force on this mass simply because it has mass, and mass number 2 is also going to be exerting a force on mass number 1 simply because both of these objects have mass. This is always going to be an attractive force, so we never have to worry about a sign with this expression of gravity. It's always going to be towards each other. And I'll also just kind of point out that these are an action-reaction pair. Something to always remember is that force is a vector, and I can have multiple objects that are in different directions. If I consider this problem down here and I want to figure out what is the force on this little ball that I just colored green, and I have two other balls in the problem, then what I can do is I can first calculate this force right here, knowing the masses of those two balls and knowing the distance of separation between them, simply applying Newton's law of gravitation. Then I go ahead and I can calculate this force over there using the same equation, F is equal to big G, mass 1, mass 2, divided by the distance of separation squared. The distance of separation squared for this one is simply going to be that distance squared. And then I can combine them as we've done using vectors many times now. The weight of an object is actually going to be the total gravitational force exerted on it by all other bodies in the universe. It turns out, though, that at the surface of the Earth, all the other ones are so small compared to the force of the Earth. So we can now write an object's weight to be equal to big G multiplied by the mass of an object divided by the radius of the Earth squared. What that says is here I am at the surface of the Earth, so my distance of separation is going to be the radius of the Earth and I'll square both of those. What we're really doing there is we're treating the Earth as acting, as all of its mass acting in the center, and here we are standing at a distance of the radius of the Earth away from it. Up until now, we've written that an object's weight is going to be its mass multiplied by gravity. So you can kind of see that this value of g is going to be those terms, and if you don't believe me, you can look up the mass of the Earth and the radius of the Earth and peck all that into your calculator, and you will see that that is indeed comes out to be 9.81 meters per second squared. Using this expression right here is, a pretty good approximation. If we're a meter off of the Earth, or 10 meters, or even 100 meters off of the Earth, then we don't really change this distance of separation very much compared to the very large radius of the Earth. So for everything that we've done, it has been good and it has been close enough. However, as we start to move further and further distances away from the center of the Earth, then the acceleration due to gravity is going to change. It's going to become smaller. This figure right here shows how the weight is going to decrease as we move further and further away from the center of the Earth. If we have our weight, as I said in the last slide, we need to calculate it about the center of the Earth, and as we move further and further away from the Earth, you can see how the weight is going to decrease, and it's going to decrease like a 1 over r squared relationship. One thing to always be careful of is a lot of problems dealing with weight is actually going to tell you, say this astronaut is going to be 25,000 meters above the surface of the Earth. So it gives a height relative to the surface of the Earth. We have to always just be very careful to remember to add in the radius of the Earth as well to problems like that. The reason why we put the negative sign in for gravitational potential energy is because we want to define it more like an energy well. What I mean by that is, at the surface of the Earth, we will have some gravitational potential energy. It will be negative. However, as we move further and further away from the center of the Earth, then our gravitational potential energy becomes closer and closer to zero. And since the gravitational potential energy is equal to some constants divided by the radius, what we want at the end of the day is, as the radius becomes closer and closer to infinity, we want the gravitational potential energy to be equal to zero. We can still think about mass times gravity times height. As we increase our height and become further and further away from the Earth's surface, we are increasing our potential energy. It's becoming less and less negative. So MGH still does hold. To be able to escape from Earth's gravitational pull, we can take an object, maybe your physics book, and throw it really, really, really hard. This would be an object's escape speed, which again is just going to be how fast you have to throw an object to escape from Earth's gravitational pull. We can look at this as a conservation of energy problem, where we're going to have the book, it's going to have some initial kinetic energy before, that will always be equal to the energy afterwards. For the book, it's going to have some initial kinetic energy, K1, it's going to have some initial potential energy, U1. It has just barely escaped from orbit. You can kind of picture it as just hanging there, so it will have zero kinetic energy, velocity will be zero, and the potential energy will also be zero, thinking back to what I discussed on the last slide. So we can go ahead and we can write what these guys are. This is going to be 1/2 mass velocity 1 squared minus big G, mass of the Earth, mass of the textbook, if you will, and then the radius of the Earth. These guys will sum up to be 0. You can see that the mass of the textbook is going to cancel out. We can go ahead and we can solve for this velocity. So velocity 1 is going to be 2 multiplied by that gravitational constant multiplied by the mass of the Earth divided by the radius of the Earth. So this value right here is going to be how fast you need to throw an object to escape from Earth's gravitational pull, and the interesting thing is it depends on the object's mass and it depends on the object's radius, not the mass of the object. The other thing that we can say about this particular equation is it could apply to other celestial bodies. We don't have to necessarily say the Earth here. It could be Jupiter, it could be the Moon, Saturn, so on and so forth. Of course, this does neglect friction and everything like that, which does exist, so in the real world we do have to worry about things like that, but this is a kind of a conceptual look at it. Here I just like this graph because you can kind of see conceptually what we're talking about here and how we launch a satellite into orbit. If I stood on top of a really tall tower and I threw an object, and I threw it with not a whole lot of speed, then it's just going to fall down to the Earth. It's going to follow path 1. If I threw it, and I am throwing all these balls towards point B here, if I threw it a little bit faster, then it's going to land further away. And if I threw it even faster still, then it's going to at some point reach path number 3, where it's going to be falling towards the Earth. It's still feeling the effects of Earth's gravity. It's feeling that force. However, it no longer intersects with the Earth. It passes by the Earth. It is still feeling that force. It's still accelerating, but it just keeps on missing the Earth. The same with 4, 5. What's happening is it's just being thrown faster and faster, and so it misses Earth by more. It is still definitely accelerating. It's still feeling the force of Earth's gravity. And 6 and 7 might start to get to the ones where I've thrown it with enough velocity that it has been able to escape Earth's gravitational pull.